With our next keynote speaker. So our next speaker is Francisco Martin, lecturer and researcher of robotics at University de Juan Carlos in Spain. He's an expert in ROS and ROS2, a real ROS developer, and recently he got his latest paper published about ROS2 navigation.
Yeah, it's an amazing paper, actually co-written with Steven Nasensky. Again, that Steven is also in the conference, and he's one of the finalists of the ROS Awards. So anyway, for his presentation here, Francisco is going to teach us how to build intelligent behaviors using ROS2. And he's going to teach us about the concepts of the differences between skills, between actions, and between plans. So we are ready to start this because it's going to be an amazing ROS2 speech and lesson. So Francisco, are you ready for your presentation? Okay, great. So the audience is all yours. Go ahead.
Okay, hi, ROS developers. I'm Francisco Martin. I'm doctor in robotics and the leader of the Intelligent Robotics Lab at Rey Juan Carlos University in Madrid, Spain. I want to say thank you to Ricardo and his teams to invite me to this conference and their support preparing the ROSDevDay. It's an honor to be here with you all.
It's our honor. Thank you, Martin. Francisco.
Okay, this talk is dedicated to explaining how you can develop intelligent behavior in ROS2. In this project, we will simulate a Turtlebot 3 in Gazebo, and we will use ROS2 planning system, PlanSys2 in short, a software that I am the author. Everything we run in ROS Eloquent uses the fantastic environment ROS Developer Studio. First of all, a little bit of theory. Creating intelligent behavior is one of the main objectives in robotics. Since the 70s, many researchers have provided different approaches to achieve it. Here, I will use a layered approach, quite general and widely used in many projects. We will decompose the development of behaviors into 3 layers or levels, as you can see in this figure. The bottom layer contains the robot skills. These skills provide basic functionality and communicate directly to the hardware of the robot. It typically runs at high frequency, and it is very common to be accessed from a medium layer using actions. Actions in ROS are a very convenient mechanism for using skills. It separates interface from implementation, provides feedback info, and notifies the result of the work when it finished. Example of skills are navigation and manipulation that in ROS2 are implemented by the navigation2 package and the move-it2 package. The medium layer uses skills to implement basic behavior or task. It sequences or parallelizes the activation of skills. We can use several packages to develop behavior. We have FlexB, we have SMAC, SkyROS, or the one we will use in this project, behavior trees. An example of a task could be navigating from a room to another room, opening the doors in the way. This task involves perception, navigation, and manipulation. This task should coordinate the execution of this skill to achieve a global behavior. Okay, for many simple applications, this and the skill layer are enough. When the problems start to be more complex and the variability of the problem grows, the mechanisms of this layer do not scale very well. One solution is a higher layer called mission layer. The mission layer activates behavior or task. It finds out what is the sequence of tasks that the robot should take to achieve a goal. This layer usually uses planning to adapt dynamically to a concrete problem. In this layer, we can use ROSplan if we are using ROS1, or PlanSys2 if we are working in ROS2. Okay, let's hand on with Developer Studio. Let us start with the bottom layer, the skill layer. We will use navigation 2 as the reference package to get the skill of navigation in a known environment in ROS2. This is the documentation, the web page, and you can go to the GitHub. And the main author of this package is Steven Masensky. I'm contributing a little bit to this repo. Okay. Navigation 2 uses an action server to expose its functionality. It accept navigate to post action. Okay, this is the action. If you want to see what is the data in this action, you can take ROS2 interface. So this is navigate. It's here. You can copy this. So the goal is the the goal pose. Here in this version, you don't have feedback, and the result is empty. But in the next version, in Foxy, in the master, you can select another things in the goal, and in the feedback you get the distance to the goal. So, but here in Eloquent, this is right now the content of this action. The output of the navigation to package is the velocities directly sent to the robot base control. Okay, so let's try. In a terminal, let's type this command. It's the launcher of navigation. Here in tools, we can select Gazebo. Okay, I like to put in a separate tab. So here we have this word and the Turtle 3 simulated. If we go here to the graphical tools, okay, put here in another tab, resize, we can see the robot is represented by the transforms. We can see the map, and in this map is inflated from the obstacles in order to calculate the paths avoiding obstacles. Here in the toolbar, you have the navigation to goal button. This call directly to the action, to the navigation action. So you can select it. You can here click, drag, and you can see the robot moving here in the Gazebo. Okay. So this is the path, and this green is the particle filters, is part of the localization. Is the estimation of the position of the robot, is a probabilistic approach. So this is our first skill, is the navigation skill. So let's close this. Control C. Let's make sure that everything is closed for the next execution. Okay, maybe we have to kill this process. Okay, now let's check again. Okay, everything is closed. Fantastic. Let's go to the next layer. In the previous section, we saw an example of a skill. In the task layer, we will use a skill like navigation to develop simple tasks or behaviors. We will use behavior tree. Here is you can see the main web page of behavior trees. This is a software developed, the main author. The author is Davide Faconti, And this software is used in many projects. For example, here, if you pick in the group, you can see his video is a video from Moses. It's a European project in which they have used behavior trees. Okay, you can use Groot. This is a tool for creating the behavior trees. And you can monitorize the execution of the behavior trees at runtime, and you can create basic behaviors. Okay. A behavior tree is an excellent choice to develop behaviors. The leaves of the tree, the leaves at this is clear with communication with awesome robot behavior. The leaves of the tree can contain calls to actions for activating skills or check values received by subscription. The intermediate nodes, these nodes, the sequence, return, the successful or follow or fallback, define the flow of the behavior. There are sequences, loops, condition, among others. The basic operation on any node in a behavior tree is tick. When you tick a node, you are requesting that node to execute one iteration of its functionality. The return value of a tick is one of these values. This can be success if the node has successfully completed its task, a failure if the node failure during the execution, or running if the node has not yet finished running. Okay. Here we have some, as example, if you tick in a sequence node, for example, it ticks in turn its children. If the first child returns running, the sequence node returns running to his father. It will tick the next time it is ticked. When this child returns success, the sequence node ticks the other child. When all the children has returned success, the sequence returns success. It is until this moment it is returning running. Okay, this is another node. The fallback node will tick the second children only if the first children returns failure. It's a convenient way to manage contingencies. Behavior tree separates the structure of the tree from the implementation of the nodes. A behavior tree uses an XML file to code its structure. We can use the tool like Groot for creating behavior trees, or edit the XML directly. Here we have an example of a behavior tree. So you can directly edit this XML. Okay, I will show you a complete example of a simple behavior using behavior trees. Here is the scheme of this example. Instead of activating any skill, we will send some messages to the standard out to simulate the operation with the arm of a robot. We will create 3 control nodes. Here, approach object, open gripper, and close gripper. And this will be the library of control nodes that we can use in the behavior tree. Is here the file. And last, we have this program, is share main BT, that will read the XML and will call the tree, the root of the tree. Here we'll open the ID, and this is here in ROS2 workspace, here in SRC, ROS2 planning system examples, and PlanSys2 BT examples. Here we have the complete example I will use in this project, but here in the behavior tree XML, you have some behavior trees. Let's see the chart XML. Okay, this is the XML we will use. Okay, the implementation of this control node are quite simple. If you go here to include, and in include, you see the behavior tree nodes. Let's see, for example, approach object. Well, this is all the file. This is a class, approach object, that inherits from agent node base. It has the tick method, and this control node has a counter. This is the implementation. Is behavior tree here, approach object. This is all the implementation. So you start the counter in 0, and the first time you call to the tick, it will return running, and the next time it will return success. Okay. So all the control nodes are implemented in the same way. Close gripper will do the same, and move will do this. Move will do another thing. Okay. Let's see the chart, main BT. That is a very simple executable. It has the main, and we declare a factory. We register our custom nodes in the factory, and we create a behavior tree from a file. In this case, the chart.xml file. Once it is created, here we have a loop that runs on 1 Hz, and it will be ticking the root of the tree until it returns success. If you remember, this sequence will return success when all the children return success. So let's run this example. Row2, run. It is here. You don't want to type 2. Gripper, approach object, and close gripper. No surprise. And it's finished as soon as the last control node returns success. So you can use this approach to create basic behavior. Okay. I will open this third part. You can click in next action. We go here to the next project. Okay, let's go with the last layer. The mission layer creates plans composed of action to achieve a goal. Each action corresponds to a task in the task layer. A planner is the core of the planning system. A planner takes a domain of application and a concrete problem to create a plan. Here, the difference with the previous section is that now the sequence of action will be calculated at runtime instead of in design time, and the system could adapt to changes in the environment. Let's illustrate the explanation with a simple sample in which our robot, R2D2, must carry the pieces to assemble a car. So R2D2 should go to pick its piece and carry it to the assembly zone. And when you have one wheel, one steering wheel, and one body car in the assembly zone, you can assemble a car. Okay. We will use PDDL. PDDL is Planning Definition Domain Language. It's very similar to Lisp. It has a lot of time to specify the domain and the problem. The domain contains the declaration of the element that can be present in a concrete problem to solve. Here we define the type of instances that we can find in a problem. In a problem, we can have robots, zones, pieces, and cars. Okay. These are the valid predicates that can exist. Predicates are facts that are true if they exist in a determinate moment. When instantiated predicates, the argument, here the robot and the sound, okay, the argument are filled with the instant of the specified type. In our domain, we can apply 3 actions. Okay, this is simplified. We go here to the PDDL directory. You can see the complete PDDL file, the working file, but I have simplified for explanation. Okay. Yes, we have 3 actions. The PDDL action are move, transport, and assemble. With the action, we can solve all the problems we have. Okay. Each action has a set of parameters. These are the parameters. So when you apply move action, we have to specify which robot, the starting zone, and the goal zone. Okay. We have the condition. The condition is the robot has to be at the initial of the action in order to be applied, that we can apply this action. The robot has to be in the starting zone. And the effects is the robot is not longer in the starting zone, so the predicate is removed from the knowledge base of the planning system. And the robot now, the result is the robot is in the goal zone. Okay, that is the explanation of what is a move action here. Okay, let's go to 1 second. So let's try. Okay, here. We will run we will use 2 terminals. In the first terminal, we will run the PlanSys2, the PlanSys2 system. We will use this launch here, in which we include the main launcher of the ROS2, the PlanSys2, and we'll set the PDDL. So that is what we did here. To start this, and here in this terminal, we will use a tool in PlanSys2 called terminal. This is a terminal in which you can use the tab to see the available commands, and you can, for example, get the domain. So you can see here the domain. You can see the types. This for types. So this is not in the terminal. This is here in these windows in the PlanSys2, but you can interact in any time with the PlanSys2. You can see what are the model predicates. You can see a predicate, for example, robot at. So you can here work perfectly with this. So we will populate the problem. The problem is the concrete situation in which we want to make the plans. So we can see the instances, nothing, and here the predicates, nothing. So let's populate this. You can directly copy and paste in the terminal. Here you have this, so you can directly copy and paste. So in this way, we have several instances. We have here this instance is R2D2 is a robot. The wheel zone is a zone. Steering wheel zone is a zone. Body car zone, everything. Assembly zone. We have 4 zones, and we have 3 pieces: wheel 1, body car 1, and steering wheel. Okay, so you can see get problem instance predicates. Sorry. Oh, this happened that day. No problem. I don't know why. Let's start again. Start again. Populate a gate with instances. And predicate. Okay, get problem predicate. Now it's working perfectly. We have these predicates. PSAT, wheel 1 is the wheel zone, body car 1 is in the body car zone, the steering wheel 1 is the steering wheel zone. And the robot, the R2D2, is in the assembly zone. So everything is correct. And now let's plan. So let's establish a goal. This is the goal. We want that the piece that currently is in the wheel zone, we want that this wheel will be in the assembly zone. So this is the goal, and this is the plan. If you type get plan, you get the plan, but you don't run it. Okay? So the plan is R2D2 has to move from the assembly zone to the wheel zone, and then transport the R2D2 must transport the wheel 1 from the wheel zone to the assembly zone. Okay. Okay. So we will. I will show you a more complex sample that involves navigation. So we will close here. Control D. Control D. You close this terminal, and Control C. Control C. Control C. You stop everything. Okay. I will explain the next example. Okay. This is the application we will see here. This is the skill layer in which we have ROS2 navigation and the standard out to simulate the calls to the skills. The control node libraries we will use are move, approach object, open gripper, and close gripper. I'll show you before the approach object, open gripper, and close gripper control node. You saw that they were very simple. And here we will use another control node, is move. Move will call directly to the navigate to pose action. So if we go here, I will show you the move. This is the control node move. This is inspired in navigation 2 source code, in which we inherit from the BT action node. That is you are specifying that this control node will call an action, and in this case it will be this action, navigate to pose. Okay. You have a input port, is a goal, because in behavior tree you have a blackboard. Anyone can write in the blackboard, and you can read from the blackboard using this identifier. And let's see the implementation. It's very, very simple. In the constructor, you establish what is you set the name of the action. And the first time you tick this control node, you extract from the blackboard the goal, is a pose stamped, and you set the field pose of the action with this position. Okay, this will be this action. Okay. Is the action I show you at the initial of this talk, and this is the implementation of this control node. Okay. In the plans, we will calculate the sequence of action to achieve a goal. That those actions will be move, transport, and assemble. If you remember the PDDL here, the move action, the transport action, and the assemble action. These actions, for every action, we'll have a node, a ROS2 node, and those actions will load a behavior tree. So the move action will load the move.xml. This is a behavior tree. This behavior tree contains only one control node, this move, that we call to ROS2 navigation. The transport action will have the transport XML behavior tree that uses all the control nodes, and the output will be a standard output of our navigation. And the assemble is another behavior tree that uses this. Let's see here in the code. This is the move behavior tree. This is redundant because we have only one control node in the sequence, so we could remove the sequence. This is the transport. The transport, you open the gripper, approach to the object, close the gripper, move to the goal position. This is how we specify the entry in the blackboard, and open the gripper when you are in the position. And this is assemble. It's only to simulate an assembly. Open gripper, approach object, and close gripper. Here we have the implementation of this, the move action. This is a PDD action. This has to be implemented as an action, and it's here. Move action node. In move action, you call to the constructor with the behavior tree. Is move.xml. You have to in the factory, you have a attribute member called factory. You have to register the node in the same way we did it in the first, in the other layer. And here we have a structure to connect the identifier of the zone with the geometry pose stamped. We start this here. We have the wheel zone that the coordinates are these. We have the steering wheel zone. These are the coordinates. We have the body car zone. These are the coordinates. So when this action is activated, this is the code to activate it. We extract from the argument of the action, from the argument 2, the waypoint to navigate. So what is the connection? Why the argument 2? Because if we go to the PDDL, if we see move, the action move has these parameters. The 0 is the robot, the 1 is the starting zone, and we are interested in this, the 2, the parameter 2, that is the goal zone. So we get the argument. This will be the position, the metric position, and we set the goal in the blackboard here. We are setting, sorry, here in the move. We are setting this right now. So you will set the goal pose, and everything start to work. Okay. So let's run it. So here we will follow the commands. Is it here? Okay, here. This is here. In a cell, you type this. I remove it. No, it's here. You see this, and the other, you will type this, and in another cell, the terminal. So here, the simulation. If everything goes well, and I can, okay, have the simulation. Here, here, we have the RVs information. And here, this is more or less where the robot is the assembly zone. Here on the left is the body car zone. Here is the steering wheel zone, and this is the wheel zone. So the robot, you will see the robot moving to achieve the move action. The move action. So here, yes, I know. PlanSys2 with the example. And here, the terminal. The same way we did some time ago. We add some instances. We have some predicate. Now we have more predicates because it's complex example, and not much more. You can see where the piece is, that the piece is not used, something for the planning. And you establish the goal. We want the car one being assembled. Okay, let's see what is the plan. It's very complex plan because the robot has to go to the assemblies, to the body car zone, transport the body car zone to assembly zone, then go to the steering wheel zone, take the steering wheel to the assembly zone, and do the same with the wheel zone, and then assemble. So let's run. Let's see. So this is performing the first. The robot is moving to this zone. Let's see the output. Navigation succeeded. And then, let's see. Navigation succeeded. Oh, maybe it's blocked. Okay, let me a moment to start this again. Not the simulator, only the part of the PlanSys2 terminal and the PlanSys2 system. Let's populate again this. This worked in my house.
It's going to work in this house too.
Yes, I suppose. And run. The robot is in the position, so the move will be very short. Let's see. Move. So now is the transport. You open the gripper, close the gripper, and move again, returning to the assembly zone. let's see here. Navigation succeeded. So open the gripper and move to the next position. Move to the next position. So the robot is going for the steering wheel, I think. Yes, the steering wheel. Okay, while the robot is performing the suction, I will like to say that in a real application, you will not use the terminal to do this. You can use it for debugging, for monitorize, but you will program, you will have a code like this, in which you init the knowledge, adding the instances, initial instances. You can modify the instances depending on your perception. You add the predicates using this PlanSys2 API. You can set the goal this way in another point of your code. You can execute your plan. It's a synchronous call to executing the code. And you can get the feedback of the execution of the task. So you can integrate everything we did in the terminal, you can do in your code. Current, we are transporting, we are here, no. We are here in the transport. Let's wait until the robot assembles the car. So, the gripper to finish transport. Now we will move to the last position. Move to the assembly zone for the wheels. The wheels are there, right there. The robot lost for a while, recovering. Thank you, Steven. It's recovering. Navigation succeeded, open gripper, close gripper. And we transport the wheel to the assembly zone. Maybe it has problem in this position. Some sand in the floor. Maybe I recover. So the navigation succeeded, and the last ember, and successful finish. Okay. So that's all for my side. I hope you enjoyed this project. I would like you try to understand. I know that this is quite difficult, quite hard to understand, but I would like you take some time, and of course, if you want to write me directly by email, you have some doubt, you can do it. Also, you have ROSDevDay2020 planning system here, and if you want to contribute, you are more than welcome, and you can put an issue or whatever. Okay, and that's all. Thank you very much.
Thank you very much, Francisco. Great. So now it's time for the questions for Francisco. Francisco, can you show us on the screen? Can you appear, or it's not mandatory? It's just to know you, to see you, and so the audience can also see you and so on. Great, there it is.
Hi.
Hello. And then thank you very much for the presentation. Excellent demo. Everything working in ROSDevDay2020. In ROS2. That's so crazy. And I like it very much, the explanation about the sun in this place that was making the robot a little bit slippery? How did you simulate the sand in this? Do you know?
With a lot of effort.
Okay, yeah, it's just a joke. Okay, yeah, just a joke. Very bad joke. Okay, so guys, let's go with the questions for Francisco and write down your questions on the chat. In the meantime that you are writing yours, let me ask him one question to him, and it's a very typical question that you may probably heard many times. So you are using behavior trees for creating the behavior of the robot, and then will you say that behavior trees are different from state machines? In which sense?
So, yes, absolutely. We used finite state machine, hierarchical finite machine before this, but we decided to use behavior tree because it's more flexible, more powerful. For example, in finite state machine, you cannot have in two states at the same time. Here in behavior tree, you can parallelize the execution of some action nodes. So it's an advantage. You separate the implementation of the control node from the structure. So changing the real behavior of the robot is very easy, only manipulating the XML. And sometimes if you want to modify or you have to adapt to any situation in finite state machines, many times you get a spaghetti code. And I think it's much better, much flexible to use these behavior trees.
Yes, and actually the behavior trees, they have been adopted as the official tool for the navigation 2 in ROS2, right? In order to control the behaviors.
Yes, there is a behavior tree that controls the execution of the navigation. So you have a computed path to pose and follow path, and you can have recovery behaviors. And in Foxy, you use Foxy. I contribute with a field in the action, in the request, in which you can even select what is the behavior tree you want to use for navigating. So you can use navigation 2 for going from one position to another position, or having another behavior related to navigation, of course. For example, following a person. I'm working on this. Actually, Steve pinged me yesterday to finish that pull request.
Okay. Okay, great. Waiting for it. Also, before going to the questions of the public, of the attendance, then remember that Francisco mentioned that he will accept to the Plan2 system to your pull request and your modifications. You are ROS developers, so what are you waiting? And also you can decide among all the different projects that we are showing here today. So think about contributing to Francisco's Plan2 system. And now here we have a question from, what is the question? From Frank Emerson that says, what are the best graphical tools for visualizing the state space and monitoring the state transitions?
In behavior trees, of course, is Groot.
Groot is the one that you have mentioned at the beginning of your presentation, right?
Yeah.
Yes.
Yes, it's a fantastic tool.
Yes. So you can find more information on at the beginning of the ROSDevDay that he has mentioned, even showing you how it works with a video and so on. Then we have another question from Florian Gram says, awesome talk, Francisco. And he says, any plan of giving the predicates go via XML or some other interface?
Not right now. We are using PDDL because PDDL is the language for planning. Actually, it's very usual in the planning world. There are many contests in which they set the problem, and it's a contest for planners, for people that research in planning, and the language used is PDDL. And if we want, for example, to use another planner, if we maintain PDDL, we can change the planner because PDDL is a standard in the planning for planners. So I think we will maintain this, but maybe we could we could develop some high level tools or representation to help the developers to implement these behaviors. But at final, you have to generate PDDL.
Okay. So far PDDL then. Then we have here a very interesting question from Jonas Moura. He says, how PlanSys deals with urgent states, like for example, when a humanoid robot starts to fall while following a plan?
Yes, that are very good questions, because PlanSys doesn't care about that. Because of the composition we did in skill, in task, and in plans. Maybe this is something that the lower layer, the skill layer, or the task layer has to deal with. Not the plan. The plan can detect that the robot has broken or something like that, include predicates, and the next time you create a plan, you have to replan and take some high-level action to recover. But I definitely think that this is something for the skill layer or the task layer.
Yes, that sounds more like a subsumption architecture in artificial intelligence. So those reactive layers should be lower in the architecture. Yeah.
Yes. Subsumption is a little bit different, but see, yes, more or less.
Okay, then another one from Frank Emerson that says, how easy it is to mix state machines and behavior trees. Can Groot achieve that?
Yes, you can have one. Actually, we have it in our software architecture. You can implement one PDDL action with behavior trees and another PDDL action with finite state machines. So you can. They are independent, so you can mix it.
Okay. Then final question for you, Francisco. All of them are very interesting. So this one is, I like it because it's about artificial intelligence in real time. That says, is there a special tool or instrument to help with meta-programming those plans? So produce those plans in real time?
Actually, we are starting one European project about that. I have a project is called Planning for Papyrus. Papyrus is a model-driven tool for robotics, and we are planning to introduce models and meta models in the development of this of planning. Amazing. So we have to work on it, but we are starting.
Great. Then. So look for that project then. It sounds amazing. It's about to start, you mentioned?
I started a couple of months ago.
A couple of months.
Maybe I will go to Paris in September, October to work in the CIA, in the France Center of Atomic Energy and Renewable Energies. They are there, and I will work a couple of months with them.
Okay. Great. Okay, so we'll keep an eye on that project. And there are some other questions there on the chat, but unfortunately we don't have more time. So we have to close here and thank our speaker. Thank you very much, Francisco, for your awesome presentation. Thank you.
Thank you, Francisco.
Thank you to you.
Thank you. If you want to go to the chat afterwards, if you have time, then maybe you can answer those guys. Those questions. Thank you.
Great. So